इसमें भी तो towhee है ना, उसको देखेंगे। अच्छा सर का भी पड़े।
Okay, so welcome back after the post-meet session. So we have 1 hour hands-on session start. Before that, I would like to introduce the resource person, Dr. Anand Bharti. So he is a faculty at BITS Nosta. So prior to that, he was also involved with IOCL. He worked for I think 5 years in the corporation in Haldia. And so he has experience in refinery operation also. So primarily his research areas encompass the separations, the environmental engineering, and machine learning and reaction engineering and catalysis, to name a few. So from now on, from today, second half, today's lecture including, and then again on Monday, so we will do a set of his tutorials. So I think our tutorials can come in maybe the tutorials have been circulated, right? In your WhatsApp group. Just check. So those are the problems that will be taken up one by one. So the theory you have already done in the previous lecture. Now it's the time for hands-on session. So with this, I again extend a warm welcome to Dr. Anand Bharti, and I invite him, request him to start the lecture.
First of all, you need to check whether this towhee is installed with PC or not. So you can check the towhee installation in C or D drive, na? In C or D. D drive. Check your D drive. If it is there, yes. Installed or it is installed. If it is installed, you go to CMD. You start CMD. From the start, you start CMD.
CMD panel.
From CMD, you go to the towhee folder. But if it's not in C folder, it might be in D or E or F. Whatever it is there, you can find towhee folder. And in towhee folder, you find source. Sir? In source, you first see how to go to the towhee folder. So for that, you have to first open the CMD.
It is not that same folder you will be having. Okay. D folder.
So D or E or F. Manually, you first check in which folder towhee is there. Yeah. D, D, E, F, whatever it is. And then open your this CMD. WSD. Okay, one by one. Then in the CMD, you type WSL.
That's it.
WSL you have entered. You have this screen. Okay. Then you change the folder using the CD command. Change folder, change directory. Use CD and read the towhee. In this PC, towhee is in the E drive. Right. So CD ... then CD E. CD is change direction.
Properties on 25 color text white black background white. Okay. Yes, चलेगा. आपकी application. Towhee ना?
That's you will find in your drive this towhee folder where the towhee is installed. Right now. Inside this, you first check in the towhee folder. There is a folder named as source. You go inside the source. You go inside the source and you check whether towhee's executable is there or not. So this one is the towhee executable with a size of roughly 5000 KB. If it is there, it means towhee is successfully installed. Towhee source, inside the source, you just type T. Right. So from T you will find towhee. File size is 5312 KB. Get out of the directory and enter the D directory where towhee is installed. Anyone is having problem with that?
They are offense net folder.
Order is put this now. The exact concept of the system of the functions. Which I need. Recording one plus so बोले ना बाद में at least follow back कर सकते हैं. अभी यहाँ पे word करना please support it. But Is there everyone has completed? So okay. See, inside the trolley, whatever you have opened, you can make a tutorial folder for your tutorial. So make a folder in the name of tutorial. So we are going to do all the tutorials in that folder. Yeah, make a new folder.
For that you write mkdir.
You can manually also do that. Just right click, make a new folder.
The command
You need to do that.
write mkdir.
Hmm.
Then whatever the PC name or your name, you can make folder name. Inside your folder. So make folder. Inside towhee folder, write this command.
mkdir means make directory.
And whatever your PC number is there, make a folder. Click enter. So after ls, you will see that a one PC85 folder is there. Like in case whatever your PC number is, make dir and whatever the folder's name you want. So PC, whatever your number is.
So let us see there. All done. Okay.
Folder.
Let us start. See, basically, this MCCCS story is an open source Monte Carlo simulation. Right? Similarly, we have several others. Because in this, workshop, we will be learning how to use MCCCS story. So we have only, one objective, that is learn MCCC story so that we can predict the fruit. So I have already given the tutorials. We are going to use all the tutorials. Right. So as you know, already discussed, this is a open source Monte Carlo simulation code. It doesn't run on the Windows. We have to install it on the Linux system. It's really available. So these are some history. It was developed at the University of Minnesota in 1994, and from 2003 onwards, it is available at SourceForge. So from SourceForge site, you can search MCCCS story Monte Carlo simulation, and installation links are there. Installation also, it is not a simple installation. So you have to use command for the installation of Toy. Okay, all the commands are given in the installation instruction. So you see, sir has already covered various ensembles which can be used for Monte Carlo simulations. So this towhee has a capability of doing the simulation in 4 different ensembles: PT and VT, Gibbs ensemble, and grand canonicals. Right. For phase equilibria, we normally use Gibbs ensemble. So Gibbs ensemble is something if you want to study phase equilibria, we will use Gibbs ensemble. So these are the different ensembles capabilities available within the towhee. Right. Next thing is force fields. So force field, I think, have you heard force field? Fields?
Cover here, Alina. So it's a force field means how the data connected atoms.
Okay. Yeah, I have okay. I have some links.
You can just
Yes, yes. See, if you are doing any calculation, you need some equations, right now. So in molecular simulations, we need equations so that we can find the total energy of the system. The force field means equations along with the parameters. Right. So in simulation, we need these four informations. What are the different atoms in your system? Right? What are the different atom types? We will discuss what are the different atom types when we do this thing. Then what is the functional form of the energy equation? Right. And then what are the parameters of those equations? So you can, there are several, yes. So these are the, different force field already available. So if you want to do any, simulation, first you have to find the force field parameters for the molecules. Right now, and different force field equations are already available along with the parameters like OPLS, Amber, Charm, Gromas, traffic. Right. So for whatever system you want to study, first find the force field parameters. Here, some equations are there. Yes, you can see the equations. So in any molecular simulation, what we do is we find the total energy of the system, capital U. Right. So capital U is a summation of the 5 terms. Right. The first is the bond energy. So for the bond energy, we use a simple equations, spring equation Kx square. Similarly, for angle we have spring equation P theta square. Right. Then we have the dihedral terms. So a bond, angle, and dihedral are basically between the atoms which are connected with each other. If the atoms are not connected, then we calculate. If the atoms are not connected, then we calculate the van der Waals interactions, and all the atoms have charges, so we calculate the electrostatic. So these are the typical 5 interactions which we calculate in any molecular system. Right. So in each equation, see all the constants K and theta naught. Then force field parameters means we have the information about this, all the constant K's, all the theta, R, equilibrium distances, right now. Then all the epsilon, sigmas, we need all this information. We also need the information about the charge. Here. So in towhee, there are so many options, available for force field calculations. So generally, we use the Lennard-Jones potential. This one. This one. Lennard-Jones potentials, how to calculate the non-bonded interaction using the Lennard-Jones. So there is one equations. Right now, using that equation, we calculate this Lennard-Jones potential, right? And this side we have different types of name of the force fields, like OPLS. We will discuss when we do the problem. I will show you what are the different equations, what are the different parameters. And these are the different moves available in the Monte Carlo simulation. So right now in this class, sir has already discussed the different moves like displacement, volume moves, right now. So the towhee has the capability to perform different types of moves. So we are going to use some of the moves. Some of the moves are basically compulsory moves like the translation move or displacement move or rotation about the center of mass. And if you are doing simulation in NPT, there will be volume change. Right. And if you are doing the Gibbs ensemble simulation, so there will be transfer of molecule from one box to another box. So we will be using the inter-box molecule transfer. and the rest of the moves are basically specific to the system. See, in towhee, we need two only files. If you want to perform molecular simulation using towhee, we need two files. One is the input file and another is the force field. So this is the input file and this is the force field file. And this is the format. This is how the file name is written. Right. So we will first start with this towhee input file. How to make the towhee input file. Right. So let us start with this. See, what you can do is you go to the towhee folder. In the towhee folder, there is one folder with the name of examples. Go to the example folder inside towhee. Right. So inside that, you go to isobaric isothermal ensemble. Isobaric isothermal ensemble means NPT. So go inside this folder.
Use only terminal.
Yeah, much better. But then the
CD and example in towhee folder.
See, use CD, change directory. If you want to change the folder, use CD and name of the folder. So CD examples, then CD isothermal underscore isobaric underscore ensemble. Inside that, you go to any example. Let's see, OPLS. You go to any folder, OPLS propanamide. You go inside OPLS propanamide.
Which folder? The grant. ISO.
Example, isobaric. Inside that, you go to OPLS. CD name of the folder. OPLS. CD. Right. So inside this folder, you have so many files. Right now we are discussing how to make towhee underscore input file. Right now. So you copy this towhee underscore input file and paste in your tutorial folder. You manually go to the folder, manually copy towhee underscore input and paste in your tutorial folder, whatever folder you have.
That you can go from the Windows also.
Use the window. Let's go to the example. Right, okay. OCLS, right. Copy towhee underscore input. Right, click copy. And go back to the. Here is your folder. Yes.
I hope you already made this folder. Then go to the examples, isobaric and OPLS. Here everyone? Yeah. Now copy this in towhee input. and go back to the toy folder where you made the folder and paste here.
Yes, yeah, that's it. Now open this towhee underscore input using any text editor. Any text editor, whatever is installed in your PC. Use Notepad, Notepad plus plus, Notepad equal.
You can open with Notepad.
Open the folder with the Notepad. Okay. So this is the underscore input file. For this simulation, see already the format is given. For your problem, you have to manipulate all the variables. Clear? Everyone has this file. Okay. So let us see, one by one, what are the variables are there. See, what is the problem statement? So right now we are trying to simulate. We have a system. Let's say we have 100 water molecules. We have a problem, very simple, 100 water molecules. You want to find the density of this system. You want to find the density of 100 this system containing 100 molecules of water. Simple, right? So when when we do the experiment to find the density, we keep the pressure constant, right? We keep the temperature constant, as well as in the simulation we will keep the means number of molecules. If you want to find the density of the system, we have to keep the pressure, temperature, and right. So the first, see, these are the keywords. So you cannot change these keywords. So you cannot write temperature in short as temp. Right now. So the first word is ensemble. So whatever problem you are doing, in this case, 100 water molecules. So we have already identified the ensemble. So you have to write NP. Here, so whatever ensemble you have, you write. Let's say, we want to find at a temperature of, let's say the temperature is 290 Kelvin. And pressure is, let's say, 1 bar. So these two informations are already known. Right. So in the towhee, temperature is in Kelvin. Temperature is in Kelvin. Pressure is in kilopascal. The unit of pressure in towhee underscore input is in the kilopascal. Right. So 101 kilopascal is 1 bar. Okay. So first three are very easy: pressure, temperature, and which ensemble you want to use. Now the next is mole type. Right. So in this example, we have a system where we have only water molecules. Right now, only water molecules. So this variable says what are the total number of molecule types. How many molecule types in your system? In this case, we have only one molecule type, which is water. So that's why we are using the 10 mole type is equal to 1. If in your system you have, let's say, water plus methanol. So we have two different type of molecules. One is water, another is methanol. So you will write 2. So in each problem, you have to modify all these variables. Okay. Now the next is what is the number of molecules of each type? Number of molecules of each type. So in this case, we have only water molecule. So you take 100 so that we can find the result easily in this system. So you write 100. So for the system, we have one type of molecule, which is water, and the number of molecules of water is. Okay. Then next option is number of boxes. How many boxes are available for the simulation for this case? So in this case, we have only one simulation box. Right. towhee supports up to 3 simulation boxes. right? So the maximum, option available is here is 3. So we will see two different examples when n is 2 and when n is 3. In this case, we are simply doing NPT in symbol simulation to find the density of water. So we are using only n is 2. Yeah. Okay. Next is, step style. Step style. See, in the last class, in the last lecture, you have, find the value of pi, right? And that value of pi, if you remember the graph was what? In the x-axis, we have number of steps. How many times you want to perform the experiment? On the y-axis, you have value of pi. Clear, no? Similarly here, step style means Monte Carlo, has two options. One is the cycle, another is the moves. So we have two options. One is cycle or another is the move. So what is cycle? In this code, suppose you have 100 water molecules in your system, and if you define cycle, right, one cycle, so one cycle is equal to n moves. If in your system there are n number of molecules, so one cycle will be equal to 100 moves. In this case, you have 100 molecules. So when you define cycle, it means one cycle is equal to 100 moves. Or in another case, you can directly use the moves. So both options are available. So if you are using moves here, so here the n step will be how much? See, what I'm using is cycle. So if you're using cycle and it is 100, so it means how many moves? 100. One cycle is equal to n number of moves. Right? One cycle is n number of moves. I'm writing 100 cycles. So 100 cycle means 100 into 100. So if you are using moves here, so simply write 10,000 moves. That you have to decide right now what you want to use. So normally we use cycle. Right now, so use cycle and see this number depends on your result. If you are running a simulation for let's say 10,000, and if you are, in this case, we are trying to find the density. So on the x-axis, we have number of cycles. On the y-axis, we have density. Right, and if you are running for 100, water density, right, 1. And after 100, the result is still here. At this point, it means you have to increase this cycle. So this, how you are going to decide, it depends on how many steps, how many cycles you are getting in density to the experimental density. So this is not prefixed. Depending on your system, you are going to plot this graph, density versus cycle, and then you find whether your density, whatever you are getting from simulation, is close to experimental. So any question in this slide? Ensemble, temperature, pressure, molecule type, number, boxes, cycle, and this one. Oh, this is the format of this. This thing. Yes, you have to follow this format as what is written. This towhee recognize this type of format. Okay. So in the towhee underscore input, you find all these details. So for your example, you make the changes. You write here 100, take only 100. On your towhee underscore input, you put NPT, this temperature, this pressure, 100, one cycle, and make this 100. Make the changes in the towhee underscore input file. No, 100. 100 will be response system. 200 will be last system. We can say 100. So whatever towhee and score input we have taken from somewhere, now change all the inputs as per your problem state. This is just an example, na? So we are taking 100. In actual, it will, you have to take close to 25,000. Then only you will get a straight line. See, all these syntaxes may change according to the version of the software. You are going for a latest one, then you have to again check the manual whether they have changed this variable or not. All the variables name may change as per the version of the software. Okay, let us go ahead. See, these are the basic information that you have to always give. Cannot receive this information, right? Temperature, pressure, how many molecules, etc. are there. Now, in this slide, see, there are few information which is related with how you want to print your results. Right now, the first one is print frequency. So you are doing the simulation, right? So you do not want to see the result at its stage. Okay, so print frequency means what is the frequency for outputting information about the system. So you will decide after what stage. We are giving how many steps? Let's say 100 cycles. So after how many cycles you want to see the result? So at the start, the frequency will be very high, so that you can check whether your simulation is correct or not. Once you have seen that simulation is correct, then you do not want to see the information after each step. So this information depends on you, what you want to give. So by default, you put 10. So after each 10 cycle, all the results will be available in the output file. So it has nothing to do with your simulation. It is just the output of your result. It is not going to affect your simulation. Right. Then print frequency. Right. Now the next is block size. Right. So this block size is what? So you are doing a simulation for, let's say, 25,000 cycles. 25,000 cycles. And you are printing the result, let's say, after 100 cycle. So after 100 cycle, you have result available. So you have two options. Copy, all the data, put in the Excel sheet and find the average value. Right. So instead of this, if you tell the software that you make a block size of 20. Right. I'm running the simulation for, let's say, 20,000. And you make a block of 20. Right. It means 20,000 divided by 20 is how much? 1,000. So it will make 100 blocks. It will make 100 blocks, and it will do the averaging of all the important parameters. This is just the output. Instead of doing the manual averaging, if you tell it that you make a block of 20, right, do the averaging, then you print the result. So instead of looking at the individual result, you look at the average results. Right, man. Okay. So this also depends on you. Then we have another option which is known as the movie frequency. Right. So again, put some numbers. Right. What is the what is the use? We will see through examples. In this towhee underscore, if you give this use this option, it print a file with the name towhee underscore movie file. I will show you what is this movie towhee underscore movie file. In the file we have information about the positions of your atoms. Positions of the atoms, right now. And we can do the post analysis. After running the simulation, we have several analysis. If you want to do the analysis, you have to use this towhee_movie file. Right. So if you are writing 10, it means after each 10 cycle, it will print all the coordinates information in a file. And for post analysis, we are going to use this. So there is a inbuilt utility with the name of analyze_movie. We will see. We can do the various analysis. Then this is normal backup frequency. If you are running the simulation, somehow your system is shut down, so you do not want to start the simulation from the zero, right? So you put some number after 100 cycles, make a backup file so that you can restart your simulation using this file, not from the zero. Okay. So all these informations are not necessary. It is not going to affect your result right now. If you are not doing anything, so by default, some information, some numbers are there. It will use that number if you are not putting anything. Okay. Okay. So you can change the in your input file as per your problem. So you can put 10, 20, 10, 100. Some number. Give some number. Okay.
So if I say like 20 here
Mhm.
and 2000 here, so will it change the amount of time that is required for
No, this is just how you want to print the result. That's it. It is not going to affect your simulation. If you are not giving any information, it will take the default value. Not affect your simulation. Okay, next. So next is run output. See, we have so many options. This is the output information about the simulation. So if you put full, so it will give you entire information, whatever is available with the sum. So normally you put full. If you are don't know what information you are looking for, so write a full. So it will print each and every information. Otherwise, you have other options. Intermediate results. Let's say we want the density, so it will print after 100. What is the density? What is the energy? You will see the output file. You will find there are several information. Then this is the PDB output frequency file. PDB, right? So PD is basically the coordinate file. If you are doing some simulation, we have several atoms. So we need the coordinates of each and every atom. So this PDB file stores the coordinates of the atom. So as per your choice, you give this information. After what cycle you want to save the PDB of the system. Well, in the entire output file, there will be coordinates of each and every atom. And we can do the post analysis. If we have the coordinates, we can do the analysis. See, this option PDB_output file, and this this backup frequency, it may be same. You do not want to do the analysis so much, so you can simply use the backup frequency. Then we have the pressure calculation. If you're doing the simulation, if you want to calculate the pressure, so we have the option pressure_variable frequency. So we have to write the frequency. Right now. So this is the frequency for computing the pressure. So pressure calculation is basically time-taking process. So we do not want to calculate pressure at each stage. So put some frequency. Okay, run the simulation for 20 steps. Then you calculate the pressure. Pressure calculation is computationally very time-consuming. So we do not want it. If you do not want pressure, you don't use this one. See again, all the informations are not compulsory. These are just the output information. So you can make changes in your towhee underscore input file as per this. Now we have TR max displacement frequency. Right. So we are we are doing this example, water example. So we are going to use different types of moves, right? So one move will be displacement move. Displacement. Then we have rotation about the center of mass. Then we have the volume change move. So we are doing NPT in symbol simulation. So pressure is constant. So the volume will change. So we need a volume change move, right? And in any Monte Carlo simulation, these two are the common moves. Displacement moves. We want to displace the molecules inside the system, as well as we want to rotate the molecule around the center of the mass. Right. So what is these two options are? So it says maximum displacement frequency. So at the beginning, we don't know what would be the maximum displacement. So give some number. Right. So as soon as the simulation goes on, it changes this frequency automatically. So we start the simulation with some number because we don't know. Right. So we will discuss more about this in the further slides. There is a criteria which is known as the acceptance rates. If you are doing the simulation, right, and if you are saying, okay, we have a displacement move. When we are making a displacement move, so we also give the target. Okay, let's say we are making 100 moves, 100 displacement moves, and the target normally is 0.3 to 0.5. What is the meaning is, if you make 100 displacement moves, so all the moves are not successful moves. All the moves are not successful. Only successful moves are in the range of 0.3 to 5. When we are doing the simulation, we do not want each move to be successful. We want 50%, close to 50%, similar to the tossing the coin. 50% head and tail. Right now. So in the start, we don't know what would be the target. So you give some number, you do the start the simulation, right? If let's say if in the initial success rate is 90%, right? So this code will automatically increase the delta, this max, delta max. What is delta max? So we have some atom. Right? So in the beginning, we give the information. What would be the maximum displacement from negative to positive? So this atom can move from this distance to this distance in single move. That is your delta x max. Right now, if the acceptance is very high, let's say acceptance is very high. So what you will do? You will increase the delta x max or you will decrease. So we have started the simulation with some delta x max. Delta x max is the maximum possible displacement in a single move, right? But your acceptance is very high. It means delta x max is small, so increase it. So this code will automatically increase it because we have given the information that our target acceptance rate is 50%. So it will automatically increase. If the acceptance rate is very low, it means delta x max is very large, so it will automatically decrease the delta x max. Clear? So we have two variables, maximum displacement and maximum volume displacement. So after see, this code is not going to update this delta max after each stage. So we have to give the frequency. So 10 means after 10 steps, it will update the delta x max or delta volume max. And after 1000 cycle, it will be constant. Only in the initial you have a problem. After that, it will be constant. So if you are not giving any information, so the software will take the default values, and it is again not going to affect your result. This information is not going to affect your final result. So any question in this point? Yeah. Right. So yes, after this, we have in important variable which is known as the limit. Limit. So we have only logical two options, either true or false. Either true or false. True means I am telling the towhee to generate the position of all the atoms. To start the simulation, you need the position of all the atoms. So we have two options. Either towhee will generate it, or if you have already have the PDB files or the position of all the atoms, make it false. If you make it false, so it will start the simulation from towhee underscore initial file. In the towhee underscore initial file, I will show you already all the atoms positions are. So when we are starting the fresh simulation, we make it true because we do not have the position of coordinates. If you are rerunning the simulation, so this limit true is not required because we already have the backup file. So we are going to start the simulation from the backup file. So write it false. So this one is important. Limit. When you're doing a fresh simulation, and if you do not have a PDB file of all the coordinates of all the atoms, you write true. towhee will generate the position of all the molecules. Clear? If you have the PDB file from some other sources, we can make the PDB file from other sources also. Or we can use the backup file which is generated by towhee as an initial file for the next round of simulation. Then you write it false. So this is important. Done. Next is init box time. If you are writing init true, it means towhee is going to generate a box with some number of molecules. So you have to also mention what would be the dimension. Here we have basically three options. If you are using init box type, we have three options. One is the dimensions, number density, unit cell. The simplest one is the dimension. You give the dimension of the simulation box. If you are using this information, it means as a user we are going to provide the information about the dimension of the qubit boxes, length, height. So these are the easiest option. So this you have to remember, limit true or false. Any question? So you can make the changes as per the problem. Check whether limit is true or false. It is false. It means in the folder there is already file. So make it true. Make it true. So it will generate the water molecule position. And in the init box type, write dimensions. See, all the variables and all these, these true dimensions are, inbuilt defined variables. So we cannot change these dimensions. We have to write dimensions. What is step?
Our file we are having that one line before that we are having one line that is same for first step.
No, delete that one. That is not required for our simulation. Yeah, this is chemical potential. So chemical potential is not required. That is for MUBT. So this is a general file. So you remove this state part, whatever is there. That variable is not required. See, again, whatever we are discussing only limited to the NPT simulation. If you are now going for the Gibbs ensemble or MUBT, so again some new variables have to be added. So we are going to see each of them one by one through different examples. Right now we are only doing NPT ensemble. So if you are doing NPT, this is the part. For others, new variables will be. Okay. Next. This is also init style. So init style we have so many options are there. Init style you understand and init initialization. Initialization. So this towhee is going to initialize. We are going to provide the box dimension, right? Similarly, full CBMC, we will discuss what is CBMC. CBMC is one algorithm. Using this algorithm, molecule is basically created. How the software is going to create the molecule? So there is one algorithm, which is known as the CBMC, configurational bias Monte Carlo. So this is one algorithm. Using that algorithm, it is going to create the molecule inside the box. We will not discuss the algorithm. So simply use full CBMC. Next is init lattice. So in molecular simulation, we are simply using the cubic boxes. Cubic boxes. So write simple cubic. All these are almost, in each simulation, all these will be constant. It is not going to change. We are always doing the simulation in the cubic boxes, so it will be simple cubic. If you are going to make the molecules, simply use full CBMC. Okay. Next. Now this, this information we have already used at the start, but we have to again use this information 2 times in the input file. So this is the initial number of molecule. So write 100, whatever you have. So that 100 must match this 100. Then we have the, coordinate of the boxes in X, Y, and Z dimension. And all the lengths are in angstrom. So box size in angstrom. Right. So I'm giving a box size of 888. So see, here is the point. So you cannot give any number. See, the total number of, you see in this example, so total number is 400. Right. So you have to give a box size like 8 into 8 into 8. This must be greater than this 400 number of molecules. We have predefined, let's say 100. So you have to define a box size, is a cubic box. So X equal to Y equal to Z. So put a number so that their multiplication is greater than the number of molecules. In your case, if it is 100, so 555, 125. You cannot use 444. Or any number which is greater than 100. We can also use 10, 10, 10, 8, 8, 8. So this point you have to remember how to give the box size at the initial stage. And the unit is in angstrom. So multiplication of X coordinates, Y coordinate, and Z coordinates must be greater than the initial total number of molecules. The total number of molecules. Then 1 minute. This is not the length, right? Please write. This is not the length. Huh? Length is here, right? So this is the number of molecules. This is not the length. Not the length. Length is here. This is the number of molecules. So total is 400. So this simulation is going to put 8 molecules along the x-axis. Right now, 8 molecules along the y-axis, 8 molecules along the z-axis. There are 2 types of algorithm for putting the molecules in the system. One is the random approach. This one is the systematic approach. It is going to put the molecule one by one. So this is not the length, right? This is the number. So that's why this multiplication has to be greater than this. Box length is here. H matrix. So box length is given in the form of a matrix. Since this is a cubic box, so you have to only fill this diagonal one. And the rest others will be 0. For cubic boxes, we have to only fill the diagonal. So here I am giving a box length of 25 angstrom. So how do you are going to decide this box length? But how, suppose in this case, I have given 25, 25, 25. How you put any system, you will put a number. 25 is the maximum length of the box. It is 0, 0, 0. So an extraction 25, 25, 25. See, if you know the density of your molecule, so based on the density, you can decide this quantity. That's it. Suppose we know the density. Cubic. Is it cubic box? See, you know the numbers. Number of molecules that this number has to be decided by you. How many molecules you are going to put in the system? You know the n. Take some V. This is V. V is LQ. So you have number by volume. Right now, so if you have the number that is molecules, convert that into moles. Then you convert that moles into mass. And then you have the volume. So density is mass by volume. So density, see, you have the capital N. This is number of molecules. Convert this into moles. Divide by the Avogadro number. That is your moles. Then you know the molecular weight. Convert into gram. So this is fixed. You are not going to change this N. Only change is the volume. So you take some volume. Let's say 25, 25. So you will find some density in angstrom cube. Right, we convert this angstrom cube into cm cube. Right now, then you find density. Density is this gram by cm cube. If you are starting your simulation close to this row, so you will achieve the state of equilibrium in few steps. Right now, if let's say you have done this calculation, and for the calculated system, your density is, let's say, 1200. So it will take few steps to equilibrate your system. If you are starting a simulation, you have randomly, you can even give the 100 angstrom. So there is no issue. Final result is independent of this box size. Right now. So if you are giving, let's say 100. So let's say you are starting with 200, density of 200. So from 200, it has to go up to 1000. So it will take more time. In molecular simulation, you know the molecule, you calculate the density, you have the density, you take some box length, then you calculate the density and make sure that your calculated density is close to the experiment, so that you can reach your this equilibrium state in 2 steps. Otherwise, in one case, it will, let's say, it will take few hours, and another case it may take few days. So this number has to be, calculation has to be done. Yeah. Okay. So these 3 informations are important. So in any simulation, you have to put all the 3. Yes. So this is the one part of the input file. You check your input file. So this is the one part. So in the input file, basically we have 3 sections. So this is the one section. Here, we are giving information about the box sizes, temperature, pressure, number of molecules, which symbol you want to use, along with some printing information. What information you want to print at what interval. So this is one section. Lunch break. Lunch break. We can explain.
This actually complete setting.
One section is complete.
Section is complete.
Not input. One section of the.
One of the file is complete.
One.
So other files are there.
Mhm.
Take a lunch break, and then again after
Then we will.
that you can just. lower density, so you start with lower density.
Ah.
So if you convert.
No, this is not GUI. It's completely based on Linux. So you have to write all that.
Initially,